Every time a program reads from a file or a socket, it asks the kernel to do it. A read, a write. Each one is a system call, a trip across the boundary between your program and the operating system. For decades, that was fine, one trip per operation. But look at modern hardware. A single flash solid-state drive can now handle over 1 million input-output operations every second. At that speed, something strange happens. The work of doing the read shrinks. And the cost of asking, crossing into the kernel and back, 1 million times a second, starts to dominate. The boundary itself becomes the bottleneck. So what if you didn't have to ask every time? In 2019, Linux shipped an answer. It's called I/O Uring, and it's quietly replacing epoll as the foundation of fast input and output. Let's look closer at what a single read actually costs. Your program runs in user space with limited privileges. The kernel runs underneath with full control of the hardware. A system call is the doorway between them. To make one, the processor switches modes, saves your registers, and jumps into kernel code. On the way back, it restores everything and switches back. That was never free. And after the Spectre and Meltdown attacks of 2018, it got more expensive. The standard fix, kernel page table isolation, forces the processor to flush part of its address cache on every crossing. Now multiply, 1 crossing per operation. 1 million operations a second. The overhead of just crossing the boundary grows until it crowds out the useful work. This is the syscall tax, and the readiness model of epoll, for all its cleverness, never escapes it. If you've ever built a high-performance server, you know epoll. Epoll follows the readiness model. You hand it thousands of sockets and ask, which ones are ready? It replies with the handful that have data waiting. That was a huge leap over checking every socket yourself. But notice what's left behind. For each ready socket, you still call read yourself. Epoll tells you which door to open, you still pay the crossing to open it. The system call per operation never went away. And there's a deeper limit. Epoll only works for things like sockets and pipes. A regular file on disk is always reported ready, even when its data isn't in memory yet. So epoll can't drive disk reads at all, and Linux's older asynchronous file interface was notoriously clumsy. We don't want to be told when to act, we want the kernel to act for us. Here is the idea that changes everything. Picture user space on top and the kernel below. Between them, I/O Uring places a region of memory that both sides can read and write, shared memory, mapped once when you set things up. On that shared region sit 2 ring buffers. The first is the submission queue. You write your requests into it. Do this read, send this packet, open this file. The second is the completion queue. The kernel writes its results back into it. That's the whole shape. You drop work into one ring, the kernel leaves answers in the other. Because the memory is shared, handing work back and forth copies nothing. And in the best case, it doesn't require a system call at all. 2 queues, 2 directions. Now let's see how a single ring actually works. A ring buffer is simpler than it sounds. Take a fixed array of slots and bend it into a circle. Then track just 2 positions, a head and a tail. The producer writes a new entry at the tail, then moves the tail forward. The consumer reads from the head, then moves the head forward. When the head catches up to the tail, the ring is empty. No locks in the common path. Now the clever part. Each queue assigns those 2 roles differently. In the submission queue, your program is the producer and the kernel is the consumer. In the completion queue, it flips. The kernel produces the results and your program consumes them. Both sides see the same memory, so they stay in sync using lightweight memory barriers instead of locks. Submitting work is just advancing a tail. Collecting a result is just advancing a head. That's the engine underneath everything else. Let's follow a single read, from start to finish. First, you grab a free slot in the submission queue and fill in the request. The operation is read, here's the file, here's the buffer to fill, here's how many bytes. You also attach a tag, any number you choose, say 42, so you can recognize the result later. Then you advance the submission tail, and if needed, you make one call into the kernel to say, work is waiting. The kernel picks up your request and performs the read on its own time, asynchronously. When it finishes, it writes an entry into the completion queue, tag 42, result 4096 bytes. You read that entry, no system call needed, match the tag back to your request, and you're done. And here's the real trick. A single call into the kernel can carry not one request, but hundreds. That last point is where I/O uring gets its speed. There are two ways to shrink the syscall tax toward nothing. The first is batching. Instead of one crossing per operation, you line up 64 requests in the submission queue and submit them all with a single call. The boundary cost from earlier is now split across 64 operations at once. The second goes further. You can ask the kernel to run a dedicated thread that watches the submission queue on its own. It's called submission queue polling. Now, when you add a request, you simply write it into shared memory and advance the tail. The kernel thread notices and picks it up. No call, no crossing. Submitting an operation becomes a plain memory write. In the hot path, the number of system calls can drop all the way to 0. The tax from before effectively disappears. Speed is only half the story, the other half is reach. I/O uring isn't just a faster read. The submission queue accepts dozens of different operations: read and write, send and receive, accept and connect, open, stat, sync to disk, even timeouts. One uniform way to ask for almost any input or output. And crucially, it covers both sockets and disk files through the very same path, the exact thing epoll could never do. It goes one step further with linked requests. You can chain operations together, accept a connection, then receive, then send, using a single flag. The kernel runs the whole chain in order, without handing control back to your program between the steps. Register your buffers and files once, ahead of time, and even their per-operation setup cost disappears. This breadth is why I/O uring is becoming a foundation, not just an epoll replacement. None of this comes free of trade-offs, and I/O urings are sharp. That shared memory bridge is powerful precisely because it lets your program and the kernel work together with very little checking in between. But less checking means a wider attack surface. I/O uring reaches deep into the kernel, and that depth has produced a steady stream of security vulnerabilities. The reaction was striking. In 2023, Google disabled I/O uring by default across Android, Chrome OS, and its own production servers, after finding it behind a large share of the kernel exploits they were tracking. And platforms built around strict isolation now restrict it by default. The lesson is balance. The same design that removes the system call also removes a safety checkpoint. Use I/O uring where raw throughput matters and lock it down where it doesn't. So let's retrace the path. We started with one system call per operation. Simple, but it taxes you on every single request. Epoll improved on that with readiness, telling you which descriptors are worth touching, but you still paid to touch them and disk files were left out entirely. I/O uring changes the model itself. Describe your work in shared memory, let the kernel complete it, then collect the results with batching or a polling thread, driving the system calls toward 0. And this isn't just theory. It's already underneath Postgres' new asynchronous input-output, inside the libuv library, and powering systems like ScyllaDB and TigerBeetle. The foundation of fast Linux software is quietly being rebuilt around two shared rings. Thanks for watching. If this made the kernel feel a little less mysterious, consider subscribing, and I'll see you in the next one.